Okay, so let's get into it. Let's get ray tracing. At the moment with WebGPU, we don't really have mainstream support for ray tracing. There are some extensions and things. What I'm going to do in this video is just show the standard sort of compute shader setup. Actually, from what I've heard, compute shaders are almost as powerful as regular ray tracing, native ray tracing extensions with WebGPU. But anyway, enough about that. Let's get this fired up. So I'm starting with a very minimal setup. We'll just start this. There we have it. We just have a simple canvas. Let me just resize that. Okay, cool. So this is what we're going to be working with. Side note, if you open this in Chrome, it will be a blank canvas because Chrome doesn't have WebGPU support yet. I'm using Chrome Canary. Anyway, so let's get into it. What we're going to do is basically, well, it wouldn't hurt to look through what we've got at the moment. Let's just stop that server. So we pretty much have the same stuff as before. We have the canvas and a few bare bones things. We do not have any pipelines at the moment. We are pretty much just doing the bare minimum, clearing with a color, and that's it. So the first step is I'm going to make a compute shader. So we can make a new, oh, maybe not a file, make a new folder, call that shaders, and inside that, I'm going to call this ray tracer kernel. Okay, and in here we're going to declare everything. So what we're going to do is we're going to take a image, a texture, and we're going to render each pixel to that texture, and then we're going to, in a post-processing pass, sort of just draw that all up on the screen. So we'll declare the texture storage. This will be group 0. Okay, group 0, binding 0, and this is super important. It's a storage texture, which is really, it's just a regular texture. So now I'm going to specify the work group size. And this is really the number of pixels which are going to be handled by this function. We want each function to handle an individual pixel. And now I'm going to declare the main function. Okay, so I'm going to use the invocation ID. This is actually basically the coordinate of the pixel that we're working on. I'm going to use that. So what we can do is just keep it super simple. Now, the reason that I'm taking this out as an int32 from an unsigned 32 is that the texture storing operation, just for whatever reason, it needs an int32, not an unsigned. Okay, so now what we'll do is make a variable pixel color. So I'm just going to reset the screen to black, and then I'm going to try a few colors and check that it is working. So, okay, we've defined the color. Now we'll just store that in the image. So that's the texture store function. And by the way, if you're wondering how I'm getting this, that is, just pop this up. This WGSL documentation, just control Fing through that and doing some searching and things. So yeah, it's all here. There are some examples. It's pretty good. It's pretty good. Okay, cool. So yeah, we're just storing that into the image. Okay, all well and good. So we'll go to the renderer and actually I'm not going to touch that just yet. I'm going to make another shader function, shader file. And this one will be the post-processing one, which pretty much draws to the screen. Okay, so here we go. So what we're doing is we take in a sampler and the texture, and we have this struct, which the vertex shader will pass out to the fragment shader. Its first position here, it actually passes to the sort of the internals, and that gets handled to the rasterizer. Now, here we could define a quad to draw on the screen, but that's sort of a less trivial action to undertake. It's not that bad in WebGPU. It's not that bad, but I'm lazy, so we'll hard code the positions and we'll reference them. So these are the 6 points for 3 triangles on a quad. Okay, let me sort of set that data. Now we have the fragment shader, which will be pretty simple. Okay, very straightforward. We simply sample from the color buffer and put that on the screen. Okay, that is looking nice. So now I'm going to head back to the renderer class and I'm going to start filling these things out. So we are going to have 2 pipelines, one for rendering, one for rasterizing the final result. So before we get into that, we're going to have a bunch of assets, and that is basically the color buffer, the image view for the color buffer, and the sampler object. Okay, we can go ahead and create these in the make assets, create assets function. Okay, so we've made the color buffer. Now it's pretty straightforward to get a view for that. and now we'll make the sampler. Nothing too technical, just a lot of typing. Okay, awesome. So now we have the color buffer view, and sampler created and ready to go. Those will be used in the make pipeline. But before we make the pipeline, of course, we need to import the shaders. So we can go up and say, alrighty, let's import them. Okay, so it doesn't really like that. We can get around it. What does it say? Cannot find module or its corresponding type declarations. Okay, no problem. We can create type declarations by going to our source folder, creating a new file, and this is called types.d.ts. And here we can declare. Okay, so we set that up. We've declared that module, and that's sort of exported all our code. So now we can read those in. So we've got ray tracer kernel, and the other one I'm going to call screen shader. Okay, cool. So now for the pipeline objects. So we're going to have a few of them. Okay, awesome. So, of course, the pipeline really abstracts the shader code and everything that we're writing, and the bind group is going to describe the resources which will be bound. In this case, for the GPU, it's pretty much just the color buffer, the texture image that we created, texture view that we created, and then for the screen, again, it's the color buffer because we want to grab that and draw from that, sample from that, as well as a sampler object. Okay, so let's head down to the pipeline, make pipeline. Okay, a little messy with all of that, but yep, there we have it. We have a single binding to that storage texture. Now we can create the bind group. So yeah, so just note that I'm not going through these in my usual level of detail. This is because, well, okay, this stuff is new, but when I do the standard shader stuff, it won't be new, so I'll just be treading over old ground. So check out the other videos or the code from those bits. So anyway, we have created a bind group layout and a bind group for our ray tracing shader. Next thing we have to do is create the pipeline layout and then the pipeline itself. Cool. So at this point, we have our our compute pipeline is created. We then need to sort of go through and create our screen stuff. So we can actually grab all of this because it's almost the same process. Not really, but almost. And yeah, let's go over it. So we have the screen bind group layout. Now we have two of these, both of which are visible in the fragment. And the first one is the sampler, and the second one is the texture. Okay, so then we have the bind group. And again, binding 0 is the sampler, and binding 1 is the color buffer. Okay, so then we create the screen pipeline layout. And then finally, being careful to make sure that we are creating a render pipeline, not a compute pipeline. And yeah, so we have layout. And then this all needs to change. So we have vertex. And then the fragment shader. And for the fragment shader, we need to specify a few other things. So we also need to specify the targets. And don't worry, if we get that format wrong, then the console will complain at us and we'll know what they're talking about. And then, why not, I'm also going to specify the primitive. Okay, so I think that's all right. I think that's all right, and we'll find out. So we can close this off. I know that's quite a big function, a lot of things. Okay, so let's go to the render. Let's sort of get this out of the way. So we have the command encoder. Now I'm going to make a pass for the compute. Okay, so we begin that. Then we will set the pipeline, set the bind group, dispatch the work, so send it out to do its thing, and end it. Okay, cool. And again, remember the width and height, we're putting that in for the size. That's the number of threads that we're gonna, number of little jobs that we're gonna break it down into. So I know we haven't really finished rendering yet, but it's probably a good point to run this and check that it's not making any errors. Because when I was running this, I would often find a bunch of errors even before rendering. Okay, so let's just refresh that. Good, no errors. Control-Shift-I, everything seems to be working. Okay, cool. So now let's proceed with the rest of the rendering. Okay, so we're actually almost done. All we need to do is get that render pass, set the pipeline, set the bind group, draw, and end. It's actually very similar to this bit, so we can even grab that. Okay, so we're going to draw. We are going to draw 6 points, one instance starting at vertex 0 and instance 0. Okay, good. So then we can end and finish, and yeah, looks okay. Let's start that up. Okay, so if we refresh that, we are now black. Control-Shift-I. Yep, it's not an error black, it is meant to be black. Let's experiment by changing the color, making sure that this is working properly. So, oh, wrong one. Pop over here. Let's make it red. Okay, so we had this black. Now if we refresh it, it's red. Okay, cool. So let's set this up so that we can draw a simple sphere. Why not? Okay, so I'm going to, first of all, we'll define the structs that we're going to work with. Okay, that's looking good. Now I'm going to just, I'll paste this in. So this is the standard sort of intersection of a ray and a sphere function. I've done this many times. For original reference, refer to my ray tracing in Python series. But what this essentially comes down to is if we were trying to solve for the t parameter along the ray, which indicated an intersection, that would come down to solving a quadratic equation. So we get the coefficients, and then the discriminant is part of it, and there is a solution if the discriminant is positive. So we'll be based on that. Okay, so now let's set a few other things up. Okay, so we get the size. And by the way, again, I looked this up on the WGSL documentation. It's texture dimensions is the name of the function. Now I sort of want to work out how far each of these positions are across the screen. Okay, so we subtract the center of the screen and divide it by the screen size in order to normalize it between -1 and +1. Do the same thing for the vertical coefficient, except that'll be based around the y coordinate, except for the normalizing factor. So the normalizing factor has to be the larger of the two dimensions, otherwise it looks all wonky. Okay, so I'm also going to define the fundamental vectors of the camera, that is the camera's forwards, right, and up vector. Okay, so we've defined those vectors. Awesome. Now I'm going to create a sphere and a ray. Okay, cool. So we've set this all up. We've got a sphere centered at x equals 3. We've got a ray, which is sort of looking forwards at the sphere. Awesome. So here I'm just going to change this a little bit. So I'll go 0.5 0.25. I'm just sort of setting some stuff. So that's the background color. And then I'm going to say, if this ray hits the sphere, then we'll change the color. And I'll take the complement of that. So 0.5, 1.0, 0.75. All right. Let me just quickly check through that. Yeah, that looks okay. Let's give it a shot. Okay, so refresh it. Nice. That's looking very cool. We can go Control-Shift-I. There's no errors. We've got it. It's real-time ray tracing in the web browser. Very cool. I'm happy with that. Anyway, I hope you enjoyed this. I hope this is useful for you. I know it takes a bit of time and looking around to see how to sort of set up a compute shader, even a simple one. So yeah, as usual, all the best, and I will see you again soon. Bye.